Hello, hello. So I'd start with a different opening. All right, in this video, we're going to be finding derivatives of log functions with bases other than e. So log functions with bases other than e would look something like this. This is the parent function for log of some numeric base a. And then this would be a composite situation of the parent function that we have here. Before we go into the calculus, let's look at the change of base formulas, because knowing the change of base formulas from before calculus is going to help us understand why the formulas are the way they are. All right, so change of base. Log base a of x. Prior to the new operating system on the 84 calculators, okay, in order for us to find this value, we would have to do change of base. Now with the new operating system, there's that template, I think it's alpha window 5. Alpha window 5. When you hit that key, so when you do that keystroke, it calls up the template that allows you to evaluate a log. But prior to that, on a graphing calculator, all we had was the LOG button, common log, base 10, and the LN button, the natural log, the base E function. And so in order for us to evaluate a log function in the past, we would have to do change of base. You may recognize the change of base formula from the previous video or right now. Log of x, log of the number divided by log of base a. And on the calculator, if we knew what the x value was and we knew what the a value was, if we knew what these two numbers were, we could just hit the common log button, do a division, and get the answer. As a matter of fact, it didn't matter if you did the common log change of base or you did the natural log change of base. We could go back to the original problem and say it's natural log of x divided by natural log of base a. And for our calculus work, we're going to focus on using this change of base version. But also keep in mind that if I knew what the a value was, the number, this would just be a constant down here, and I could rewrite as 1 over natural log of a as a constant multiplier times what's in the numerator, natural log of x, that variable. And for our purposes, you're going to see it probably more prevalent in the derivatives in this format right here. All right, let's get to the formulas of the derivatives of these two natural log situations. So if you have a function and it's a log function with a base other than e, unfortunately, this is just a new rule you have to memorize. All right, so this is kind of just the pre-work here. Now let's consider the parent function log base a of x. The first thing I'm going to do is I'm going to use a change of base on it using the natural log change of base. So this would be ln of x divided by ln of a. And if I pull out the constant multiplier of 1 over ln of a times natural log of x, I'm going to be here. All right, now I'm going to apply the derivative operator, d over dx, and that's going to result in my getting the derivative. All right, well, if we look at this right here, and it's equivalent to this function right here, 1 over ln of a is just going to be part of our derivative answer. It's the constant multiplier. And we've already found the natural log of x. Natural log of x is just 1 over x times the 1 over ln of e, which is just 1, and we're done. Okay, we might see this rewritten, though. Oops. Y prime equals 1 over... typically we put the x up front here so as not to confuse the situation where we might think we could multiply x and a in with each other. We can't, so we'll keep it separated. Well, unfortunately, they're not going to ask us to differentiate this log function, this parent log function, all day, because if they did, we're just going to keep repeating this answer. They're going to typically give us, we're going to encounter composite log functions. So instead of coming over here and doing a column situation, I think I'm going to run out of room, so I'm going to come down a little bit. All right. So let's build a composite log function with the base other than e. All right, so here we go. Y equals log base a, and u is going to be my inside function that's more than just x, where it's just another function of x. u equals f of x. All right, there's a formula for this derivative. Okay, and I'm going to share with you guys what that is after we derive it. So first let's do a change of base formula. So natural log of u divided by natural log of a. 1 over ln of a times natural log of u. So we can convert it to a e base. All right, now we're ready for the derivative. There's our constant multiplier. Let's focus on what that derivative is. We've already found that derivative of the natural log function, and it's u prime over u. So we'd have to find the derivative of u prime, stack it over u, and of course, again, we're not going to show it, but it's times 1 over the natural log of e, but that just goes to 1, so it's irrelevant. This is the formula right here that we're going to be working with. So let's concentrate our attention on this formula right here in finding derivatives of log functions. All right, so we've got the function y equals log base 2 of 5x. There are several approaches to this problem. If you want to get right to using just the formula that we have here, that's easy. The formula says my answer is going to be 1 over the natural log of base a, which in this case is 2, and I'm going to multiply that by u prime over u. For this particular problem, to go straight to the formula, it's fine, because think about what u is. It's so simple. It's 5x and du over dx, or u prime is just 5. So if I come back into the formula, I'm just going to multiply this constant multiplier by u prime, or 5 over 5x. Then you do a little cleanup. You reduce the 5's. Create a single fraction as an answer, putting the x up front, and you're finished. When the log function that you're working with has a pretty basic u, that would probably be the approach I would take. I'd go straight to just the formula. Okay, the second strategy for this, oh, let me change that to 1, maybe 1b, and this maybe would be 1a. I'm going to show you the other strategy when this is more complicated than just 5x. Let's look and see what else we might do instead. Because for our later problems, this is what we're going to want to do, this strategy. All right, instead of going right to the formula right here, why don't we do a change of base on it? So I'm still on the y, I'm not to the calculus. Let's do a change of base, which would be natural log of 5x divided by natural log of 2. And if you're able to go straight to this, 1 over natural log of 2 times natural log of 5x, that's even better. And you remember, this isn't calculus. This is just, using change of base. Now I'm ready for y prime. And actually, let me back up. Right here. This is my u still. If this is even more complicated than this, I would probably use log properties. So let's say I'm still in a y, not a y prime. I would have 1 over the ln of 2. I'd probably switch to a bracket because I'm about to apply some log properties. This could be written as natural log of 5 plus natural log of x because I'm using the product property. Not that I would probably do part B, but I'm getting you ready for the more complicated problems. All right, now so far I've not done anything but use my before calculus work to rewrite this. Okay, now if I'm going to find y prime, I've got the constant multiplier out front. The derivative of just a number, a constant, is 0. And that one's easy to find. That derivative is just 1 over x. Doing the cleanup on it, it'll look exactly like what we did in 1a. I kind of like strategy B here just because I don't have to remember a new formula or anything. That the only thing I have to memorize is the change of base formula, which is easy. And just remember my natural log derivative rule, which is u prime over u. I don't have to memorize what I feel like is an additional formula. So your choice. But certainly sometimes you're going to want to use some properties when your u expression is very complicated. All right, so let's look at 2. All right, so let's find y prime. Actually, I'm going to go back. Instead of going right to the formula, which, I mean, this one's easy. You can use the formula where this is u. And so it would be 3 over this quantity times 1 over natural log of 10. I'm going to just go follow through with my change of base. So natural log, quantity 3x plus 1, divided by natural log of base 10. Remember, in the absence of a base, it's 10. I'll probably rewrite it. Now I'm ready for the derivative. All right, so focusing our attention here, if you wanted to write out u and u prime, sometimes I write u prime, sometimes I write du dx. And so the derivative of the natural log function u prime over u would look like this. And then you restack it, make it one fraction. Let's move on to example 3. So I'm going to do a change of base. Log of cosine over natural log of cosine over natural log of 10. That's exactly like the new formula. It's 1 over natural log of a. And then I'm just going to show an extra step where it's natural log of cosine. So it's going to be your u, and then u prime. So y prime, that's a constant multiplier. To find this derivative, it's going to be natural log u prime over u. Clean up. Hard to say. Probably natural log of 10 would go first. And then you'd probably want to put that in parentheses, because if you didn't, it almost looks like the 10 is attached to the cosine. Putting cosine x in parentheses is your choice. Probably go either way. All right, I'll go to 4. Okay, now we're going to step it up a level. I'm still going to do the change of base. So it's going to be ln of this value divided by ln of 3. So I'm going to pull out the 1 over ln of 3. And I'll be left with the natural log of this expression. All right, so just think about this for just a second, though. When we go to differentiate, let's write it out over here. U is this fraction. It's pretty complicated. To find u prime, or du dx, I'm going to have to do the quotient rule. And then part of the quotient rule is going to involve my having to find this derivative. Oh, no. I'm just going to put, no, I don't think so. That's ugly. So before we find the derivative, let's apply our log properties. This is a classic problem where you'd want to use your log properties to break this apart right here to make the differentiation easier. All right, so remember this is x to the 1/2 power. So I'm going to apply the quotient log property first, rewriting that as a half. All right, and it's minus the natural log of the denominator. Make sure you're using parentheses, otherwise it's not the same. If you left off parentheses, your use of or lack of use of parentheses is critical. All right, to apply another property, log property, I'm not doing calculus, so I'm not going to make that negative 1/2 when I bring that in front. I'm still in the y function, just doing a rewrite to make my calculus easier. Now we're ready to go to y prime. Okay, peeking inside here, we have two terms, so we're going to have to apply the natural log rule to both. We have a constant multiplier here. The derivative of ln of x is just 1 over x. Here, this is our u. So u prime is just 1. So u prime, which is 1 over x plus 5. You could leave the 1 over ln 3 factored out, or you could distribute it into both terms. On a problem like this, if you were to check the back of the book or go to Calc Chat, anything like that, what you're going to see is likely a common denominator was found inside here. And once they got that common denominator, then they rewrote the answer as a single fraction with this in the denominator. And our last complicated example. All right, our objective is to find the derivative of this log base 4 with the 4th root of quantity x squared minus 5. All right, I'll do a change of base. All right, so it's the natural log of the 4th root. I'm going to go ahead and rewrite that as a rational exponent. Get rid of the radical. All right, this is a constant multiplier. For me to find this derivative, my u would include this quantity to the 1/4 power, and finding the derivative of that 1/4 power takes the chain rule. So let's still apply yet another log property here. I'm going to pull the 1/4 in front because of the log property. And again, notice I went from y to y. I haven't gone to y prime, so I'm not doing the power rule. So the 1/4 comes in front. And so the exponent is just in a new position because of our log properties. Now I'm ready to find the derivative, so I'll go to y prime. Okay, going inside here, 1/4 again is another constant multiplier. Okay, your u is as uncomplicated as it can be once we remove that 1/4. So it's 1/4 times u prime over u. 2x over x squared minus 5. Okay, so y prime equals, and this would be easy to clean up. I'm going to have 2x on top. The 4 would go in front. Oh, I'm just now seeing that I could have reduced that And then I'd probably put that all in parentheses with a quantity x squared minus 5. And just because it is quite visible, probably what I'll do is I'll divide out the 2 here and divide out the 2 here, not in this 4, but at least in that coefficient. One more thing that I want you guys to be aware of that is within your capability is you check the back of the book and this answer is similar yet different. I want you to pay real close attention to the natural log functions and the base. And what I mean is this, sometimes when you think you have the wrong answer, the authors may have simplified a natural log function. Okay, for example, pay real close attention to this value right here, not the base I said, but this value right here. So look at this 4. If you were to check the back of the book, it might not be a 4, it might be a 2, meaning if I rewrote 4 as 2 squared, just think about that for a minute. If that was 2 squared, I could bring the 2 in front here and now have a natural log of 2. So it's really kind of a simple way, it's a way to simplify your log functions. So an alternate answer, okay, would look something like this. With the 2 moved in front, it would be 4 ln of 2 in parentheses times quantity x squared minus 5. So like I said, your answer is very similar to this previous answer, but pay attention to when you're looking at the differences, pay attention to what follows ln, because if they don't have what you have that follows ln, they just simplify. Okay. So those are our derivative rules for log functions with bases other than e.